If you've ever been under a truly dark sky, far from the city, far from light pollution, it's very likely that you've seen Alpha Centauri without knowing what you were looking at. There, in the direction of the constellation Centaurus, visible to those who live in the southern hemisphere, including here in Brazil, on any clear autumn or winter night, there's a little point of light that looks just like any other star. It doesn't twinkle differently. It doesn't shine obviously brighter, although it is, in fact, one of the brightest stars in the night sky visible to the naked eye. But that little point is, technically, the closest cosmic backyard humanity has. And even so, it's as unattainable as anything else in the universe. Maybe it's easier to understand this way. Of all the billions of stars that exist just in our galaxy, this is the closest one. The most obvious candidate, the most reasonable, the most attainable, if our species ever decided to try to visit another solar system. And yet, as you will see over the next few minutes, every layer of physics, biology, and even human psychology itself seems to organize, almost on purpose, to make this journey impossible. Not impossible in the sense of, we just don't have enough technology yet. Impossible in a more fundamental way. The kind of impossibility that remains there, stubborn, even after you solve the previous problem. Let's start with the number, because the number is deceptively simple. 4.24 light years. It's the distance to Proxima Centauri, the closest star to our sun. It's part of the triple star system that makes up Alpha Centauri. It sounds small when you say it like that, quickly, as if it were a bus number. But wait a moment before moving on. Because when you really stop to feel the weight of that number, it becomes something else entirely. A light year is the distance that light travels in a year, moving at approximately 300,000 kilometers per second. That means that in a single second, light goes around the Earth more than 7 times. In an entire year, it travels about 9.46 trillion kilometers. Now multiply that by 4.24. The result exceeds 40 trillion kilometers. That's the size of the problem, even before we talk about rockets, radiation, or biology. To try to give some sense to this number, imagine shrinking the entire solar system so that the distance between the Earth and the Sun fits in the palm of your hand. Let's say about 15 centimeters. On this scale, Neptune, the farthest planet, would be about 6 meters away from you on the other side of the room. And Alpha Centauri, the closest neighbor to the Sun, would be more than 4 kilometers away. It's not a room, it's not a block. It's like crossing an entire city on the scale of your reduced solar system, in the palm of your hand. And that's the distance to the nearest star. All the others are even farther away. Now imagine the fastest thing humanity has ever built, NASA's Parker Solar Probe. At its closest approach to the Sun, it reaches speeds of about 690,000 kilometers per hour. That's about 190 kilometers per second. It's fast enough to cross the entire length of Brazil from end to end in less than 30 seconds. But if you took that probe at its maximum speed and pointed it straight at Proxima Centauri, without turning, without slowing down, flying at that record speed the whole time, the trip would take about 6,600 years. Think about what that means. The pyramids of Egypt are about 4,500 years old. Writing as we know it has about 5,000 years of history. A trip in the fastest object ever created by humans would take longer than the entire recorded history of our species. And keep in mind, we haven't even gotten to the reason why this trip would probably kill any crew member. Long before that. It's worth a side note here, just to put things in perspective. The Parker Solar Probe only reaches this record speed because it's diving toward the Sun, stealing gravitational energy from the star itself. It's not going anywhere outside the solar system. The object that's actually farthest from home, truly traveling toward interstellar space, is Voyager 1, launched in 1977. After nearly 50 years of travel, It has already crossed the boundary that separates the sun's influence from the interstellar medium itself. And even so, flying at just 17 kilometers per second, it would take more than 70,000 years to cover the distance to the nearest star. And it's not even pointed in that direction. The most distant probe humanity has ever built, after nearly 4 decades in space, is still, in galactic terms, practically just leaving home. Before talking about what exists along the way, it's important to understand what doesn't exist along the way. The image most people have of the space between stars is that of a dark and silent void. And that's largely true. But empty in this context isn't the same as the emptiness of an unfurnished room. It's the kind of emptiness that human experience simply has no frame of reference for. The average density of the interstellar medium is about 1 atom per cubic centimeter. For comparison, the air you're breathing right now, in this very room, has something like 25 quintillion atoms and molecules per cubic centimeter. It's not just a matter of being a little more rarefied. It's the difference between an ocean and a drop. A ship crossing that void will encounter almost no resistance, but it also won't find absolutely anything that can help. No cosmic gas station, no shelter, no second chance. And that's exactly where the first real problem of the journey lies: irreversibility. Every kilometer traveled toward Alpha Centauri is a kilometer that would have to be traveled back at the same speed in case of any serious, unforeseen event. Halfway through the journey, if halfway even makes sense in a trip like this, the ship would be more than 20 trillion kilometers from home and more than 20 trillion kilometers from its destination. No rescue would be possible, no resupply, and any radio message sent to Earth would take more than 4 years just to arrive, and another 4 years for a reply. The crew, if there is one, would be absolutely alone, with only what they took with them on the day of departure for decades, possibly centuries. But perhaps the most fundamental problem of all isn't the distance or the emptiness. It's that today we simply don't know how to build the engine that would make this journey possible. And we're not talking about a difficult engineering problem, the kind we haven't figured out yet, but with time and money we'll get there, like with the suspension bridge or the nuclear reactor. We're talking about a problem where physics itself seems to be working against us. In 1903, a Russian school teacher named Konstantin Tsiolkovsky, working by lamplight in a small town, decades before any real rocket left the ground, derived an equation that still governs everything we know about space travel today. Tsiolkovsky's equation relates a rocket's final velocity to the exhaust velocity of its gases and the ratio between its initial mass, full of fuel, and its final empty mass. And the relationship between these two things isn't linear, it grows exponentially. The faster you want to go, the more absurd the amount of fuel required becomes. Not just a little more, exponentially more. A chemical rocket, powered by liquid hydrogen and oxygen, the most energetic combination that chemistry allows, has an exhaust velocity of about 4.4 km/s. That number is a ceiling, not a current engineering limitation. It's a limitation imposed by the bonds between atoms. No chemical reaction can significantly overcome that. To accelerate a spacecraft to just 1% of the speed of light using chemical propulsion, the Tsiolkovsky equation requires such an absurd amount of fuel that the numbers stop having any physical meaning. Some estimates put this requirement at 10 raised to several hundred, a number so large that it can't be compared to anything in the observable universe, which has only about 10 to the 80 atoms. In other words, with chemical fuel, it's mathematically impossible. It's not a matter of money, it's a matter of the amount of mass required exceeding the mass of everything that exists. That didn't stop serious scientists from trying other approaches. At the end of the 1950s, a group of brilliant physicists, including Freeman Dyson, worked on Project Orion, an idea as bold as it was disturbing: a spacecraft that would eject small nuclear bombs behind it, detonating them one by one and surfing on the shock wave of each explosion to gain speed. Calculations at the time suggested that this type of nuclear pulse propulsion could, in theory, reach from 3 to 10% of the speed of light, which would reduce the trip to Alpha Centauri to something between 400 and 1,000 years, still longer than all of written history, but for the first time, a number that the imagination could almost grasp. The project never took off, not because the physics was wrong, but because the Partial Nuclear Test Ban Treaty, signed in 1963, banned nuclear detonations in the atmosphere. The most promising idea for an interstellar engine ever conceived was halted, not by engineering, but by a treaty about a completely different kind of fear. More recently, in 2016, a group of scientists and investors announced Breakthrough Starshot. Instead of a manned spacecraft, the proposal is to send a fleet of probes the size of a postage stamp, accelerated by an array of Earth-based lasers to about 20% of the speed of light. At that speed, the journey to Alpha Centauri would take only 2 decades. The problem is that the required laser array would need a sustained power of about 100 gigawatts, roughly the total electrical output of a medium-sized country, concentrated into a single beam. That doesn't exist yet, and even if it did, all of this applies to probes the size of a coin. None of this scales up to a ship capable of carrying humans, water, food, shielding, and everything else a crew would need to survive. Another elegant idea came from the physicist Robert Bussard in 1960, the so-called interstellar ramjet, or Bussard ramjet. Instead of carrying fuel, the ship would use a huge electromagnetic funnel to collect, along the way, the hydrogen atoms scattered throughout the interstellar medium itself, continuously feeding a fusion reactor. The ship, in theory, would refuel from the very emptiness it was traveling through. The idea captured the imagination of entire generations of science fiction writers. The problem is that when engineers calculated the numbers more carefully, decades later, the proposal ran into a scientific contradiction. Since the density of interstellar hydrogen is extremely low, again about 1 atom per cubic centimeter, the funnel would need to be hundreds of thousands of kilometers in diameter to collect fuel at a useful rate. And a funnel of that size, even traveling through the near vacuum of interstellar space at a fraction of the speed of light, would generate more drag than the collected fuel could compensate for in thrust. Instead of accelerating, the ship would slow down. The Bussard ramjet, as originally imagined, simply doesn't work. There's also the idea of the antimatter rocket, the only proposal that, on paper, would truly solve the Tsiolkovsky equation. Because the annihilation of matter and antimatter converts almost 100% of the mass into pure energy. The problem is the amount of antimatter already produced by all of human civilization, adding up decades of experiments in particle accelerators around the world. We're talking about a fraction of a gram, something in the range of billionths of a gram. A realistic mission to Alpha Centauri would require tons. The gap between what we've already produced and what would be needed isn't a production challenge. It's a measure of how far we are today from the energy scale that this journey requires. Let's say, just for a moment, that the engine problem has been solved. That somehow there is enough energy and a way to actually accelerate a real spacecraft. The space between the stars still holds another problem, silent and ongoing: radiation. And radiation here isn't just one thing. It's a family of different phenomena coming from different sources that damage the human body in different ways and don't cancel each other out. They add up. The first type is the solar wind, a constant flow of charged protons and electrons, ejected by the sun in all directions, at speeds that can range from about 400 to 700 kilometers per second. On Earth, the planet's magnetic field protects us from most of this, deflecting the particles toward the poles, where they create the auroras, the beautiful side effect of constant bombardment. Outside this protection, the particles pass through any spacecraft hull with ease and hit the body directly. Astronauts on the International Space Station which is still partially within Earth's magnetic field, already receive a dose of radiation dozens of times higher than a person on the surface of the Earth. A mission to Mars, which would leave this protection completely, would approach the career limits set by space agencies for workers exposed to radiation in a journey of just a few months. Alpha Centauri is decades away, not months. The second type is even more treacherous: galactic cosmic rays. They're not really rays. They're atomic nuclei, protons, and heavier particles accelerated to near-light speeds by cataclysmic events, like supernova explosions in distant parts of the galaxy. They come from all directions, all the time, with no predictable pattern, and they carry energies millions of times greater than any particle accelerator built on Earth. What makes them especially dangerous is their penetrating power. They pass through meters of metal, penetrate the hull of any spacecraft we know how to build today, and go through the human body, ionizing atoms and breaking DNA strands in the process. The biological consequences build up slowly and then appear all at once. Increased cancer risk is the most studied, but prolonged exposure to cosmic rays has also been linked to changes in the central nervous system. Structural changes in the brain have been observed in long-duration astronauts, and even flashes of light have been reported by crew members, even in total darkness. The result of extremely high-energy particles literally passing through the retina, with the brain interpreting this damage as if it were light. The third member of this family is the most unpredictable: solar particle events. Explosions on the surface of the sun that release, in a matter of hours, a huge amount of high-energy protons. In 1972, between the Apollo 16 and Apollo 17 missions, one of the largest events of this kind ever recorded occurred. If it had happened while astronauts were on the surface of the moon or in transit, the exposure could have been lethal. It was, without exaggeration, statistical luck. On a journey lasting decades, the chance of encountering multiple events of this kind goes from being unlikely to being practically guaranteed. Shielding helps up to a certain point. Water and hydrogen-rich polymers can absorb a good portion of the lower-energy solar radiation. But against the extremely high-energy galactic cosmic rays, shielding that's too thick creates a new problem. When interacting with extremely high-energy particles, the shielding material itself generates a cascade of secondary radiation. At a certain point, you stop reducing the damage and start trading one type of damage for another. And every extra layer of shielding is extra mass, which makes the already unsolvable fuel problem even worse. The two problems aren't independent. They're tied to each other. There's also a danger that's not exactly radiation, but it's close to it: dust. The interstellar medium, besides isolated atoms, carries microscopic grains of dust, remnants of stars that died billions of years ago. At low speeds, this is irrelevant. A grain of dust is just a grain of dust. But in a ship traveling at a significant fraction of the speed of light, the kinetic energy of impact from these is no longer negligible. A grain of dust the size of a grain of sand, colliding with the hull at 20% of the speed of light, carries energy comparable to that of a small artillery projectile. On a journey lasting years, with a ship crossing trillions of kilometers of space, the probability of multiple impacts like this is no longer hypothetical. Thicker frontal shields help, but again, every extra layer of protection is extra mass. And extra mass means the fuel problem gets worse again. Now, suppose a ship with perfect armor, the impossible engine problem already solved, and a perfectly clean void free of dangerous particles. Even so, the human body, left alone in zero gravity for long enough, starts to fall apart. This is not speculation. It's one of the most well-documented phenomena in space medicine, studied for decades aboard the International Space Station, and before that, the Russian space station Mir. Astronauts who spend 6 months in microgravity return to Earth physically different, in ways that require months of rehabilitation and, in some cases, never fully reverse. The first system to react is the skeleton. Without constant gravitational load, bones lose mineral density at a rate of about 1 to 2% per month in the most affected regions, hips, lumbar spine, and legs. After 6 months in space, an astronaut's bone density in these regions can resemble that of a person decades older. On a journey lasting years or decades without effective countermeasures, the accumulated bone loss would be incompatible with the simple ability to stand upon arrival at the destination. The heart and muscles follow a similar pattern. Without the constant effort of resisting gravity, muscle mass progressively declines and the heart muscle itself weakens. Studies with long-duration astronauts show measurable changes in the shape and strength of the heart, which starts to pump with less force because, in zero gravity, the body's fluids already move upward effortlessly. Several astronauts report almost fainting when standing up again after long missions. In a way, the heart forgets what the planet demands from it. Exercise helps, but it only helps partially. Astronauts on the International Space Station train for 2 to 3 hours every day just to slow down these losses. On a decades-long journey that represents a huge portion of the crew's available time and caloric energy. Resources that also need to be calculated and loaded from the start. Then comes the redistribution of fluids. In microgravity, the body's fluids migrate upwards. Chest, neck, head. Astronauts describe the sensation as being upside down all the time. The face swells, the sinuses get congested, and intracranial pressure increases. Sustained for months or years, this pressure affects one of the most sensitive structures in the body, the eyes, in a condition called spaceflight-associated neuroocular syndrome. Identified and named only in the last decade and a half, it flattens the back of the eyeball, compresses the optic nerve, and causes structural changes in the retina. Studies with long-duration astronauts show that most of them have some degree of these changes. And in some cases, the loss of visual acuity is not temporary, it's permanent. The immune system also suffers. In zero gravity, the immune response seems to weaken, and latent viruses in the body, like those that cause cold sores, reactivate more frequently than in people on Earth. A crew decades deep in space with no possibility of medical resupply, facing reduced immunity and reactivated viruses, creates an extremely fragile medical situation. A solution often proposed for all this biological wear and tear is hibernation. Putting the crew into some kind of induced sleep with reduced metabolism for most of the journey. It's an elegant idea, and science has already made real progress in that direction. Some mammals hibernate naturally, and research with torpor induced by controlled cooling has already shown preliminary results in laboratory animals. The European Space Agency and NASA have already funded serious studies on the subject, precisely with long-duration missions within the solar system in mind. The problem is the scale of the leap. Making an organism enter a state of torpor for a few weeks under full medical supervision is one thing. Keeping a human being in hibernation, safe, without catastrophic atrophy, without the risk of ice crystals forming in the cells, without organ failure, for years on end, decades, is a technology that doesn't exist today, not even as a functional prototype. And even if it did exist, hibernation wouldn't solve the radiation problem. The hibernating body would still be exposed to cosmic rays the whole time, only without active medical supervision to respond to an emergency. It would reduce metabolic wear and maybe the psychological stress of experiencing each day of the journey consciously. But it's by no means a complete solution. At best, it's a way to trade one set of risks for another, slightly smaller one. And then there's the mind. Isolation and prolonged confinement produce well-documented, recurring psychological effects that no amount of training or rigorous crew selection can completely eliminate. The so-called third quarter phenomenon, a pattern of increased conflicts, lowered morale, and deteriorating behavior, observed in the final stretch of long and isolated missions. It has already appeared in winter expeditions in Antarctica, in submarine crews, and in long-duration space missions. It seems to be a characteristic of the way humans respond to prolonged confinement, not a personality problem of a specific group. Selecting better people does not eliminate the effect. Training more doesn't either. We have some real, albeit imperfect, laboratories for this kind of tension. The Mars 500 experiment conducted between 2010 and 2011 isolated 6 volunteers inside a closed module with no physical contact with the outside world for 520 consecutive days, simulating a round trip to Mars. Even knowing they were technically on Earth, just a few meters from help, the participants reported episodes of conflict, social isolation within their own group, sleep disturbances, and a decline in performance throughout the mission. Precisely the kind of pattern that researchers at Antarctic bases had already been documenting for decades in teams that spend the winter isolated at stations like Concordia in Antarctica, where months of total darkness and complete isolation produce depressive symptoms and irritability. And the already mentioned third quarter effect in an almost predictable way. Even the Biosphere 2 experiment in Arizona, where a team lived sealed inside a glass structure for 2 years, ended up marked by internal divisions within the group, leadership disputes, and, in the end, a split so deep that the participants themselves divided into factions that barely spoke to each other. And keep in mind that in all these cases, there was a way out, a door, even if locked by protocol, that led back to ordinary Earth conditions, to normal air. There is a real possibility of human contact, even if it's never used outside the experiment. On a generation ship heading to Alpha Centauri, that door simply doesn't exist. There is no end to the experiment after 520 days. There's only more wall, more hull, more emptiness for decades. Now imagine a crew 20 years into the journey with another 20 ahead of them, with no possibility of return and no communication that wouldn't already be outdated. In addition, with bodies already carrying years of accumulated physical deterioration, this is the real experience behind the numbers. There is, however, a unique place in physics where the universe seems, for a moment, to offer some relief. Time dilation, predicted by Einstein's special theory of relativity. And for a moment, looking from a certain angle, it almost seems like a solution. The idea is this: time doesn't pass at the same rate for everyone. A clock moving at high speed runs slower than a stationary clock. Not as a flaw, but as a real feature of the geometry of space-time. The faster an object moves, the more time dilates for everything on board, compared to everything left behind. The numbers are impressive. At 90% of the speed of light, time on board passes at about 44% of the rate of time on Earth. At 99% of the speed of light, it drops to about 14%. At 99.9% of the speed of light, it drops to just over 4%. The closer you get to the speed of light, the more intense the effect. And in theory, a ship traveling fast enough could cross the 4 light years to Alpha Centauri, while on board only a few years or even months would pass. This isn't science fiction, it's physics measured directly. Atomic clocks on board airplanes and satellites have already accurately recorded exactly this kind of difference predicted by relativity. For a moment, it seems that the crossing could, in fact, be survived. Not by the civilization left behind, but by the crew itself, who would age slowly and arrive perhaps old, but alive. And then comes the other side of the coin. The speeds required for time dilation to really matter. 90%, 99% of the speed of light demand amounts of energy that make everything we've discussed about fuel seem modest. Tsiolkovsky's equation, already impossible at 1% of the speed of light, becomes so far beyond impossible at 99% that the numbers lose any physical meaning. In simple terms, time dilation is real, it's theoretically available, and it's unattainable in practice. The universe offers the gift and puts it behind a door that the laws of physics, as we know them today, cannot open. At this point in the conversation, someone always brings up wormholes, hypothetical shortcuts through the very fabric of space-time that would make distance irrelevant. And it's true that Einstein's field equations mathematically allow for this kind of structure. But existing as a mathematical solution and existing as a real physical object are completely different categories. No wormhole has ever been observed. The so-called exotic matter needed to keep them stable, enough for a ship to pass through without them collapsing instantly, has never been detected. And some calculations suggest that their existence would require violating basic physical principles, like negative energy, in amounts that current physics doesn't even know how to conceive. Wormholes are, today, less of an engineering proposal and more of a mathematical footnote that the universe may never intend to honor. There's even an extra cruelty hidden in that. Even at speeds where time dilation is already noticeable, let's say 50% of the speed of light, every hydrogen atom floating in the interstellar medium starts hitting the ship's hull with cosmic ray energy simply because of the relative speed. In other words, the faster the ship goes to take advantage of time dilation, the worse the radiation problem itself becomes. The two make each other worse. Let's say finally that all the physics has been solved. Engine, fuel, shielding, body, everything. There would still be the strangest problem of all, and perhaps the most difficult. The problem of human time. Not the relativistic time of clocks that slow down near the speed of light, but the ordinary time of institutions, of memory, and the question of what keeps a group of people united when the purpose that brought them together is older than anyone alive who can remember it. Someone, at some point, would have to decide to leave. A government, a coalition of countries, or some wealthy and visionary institution capable of funding a project of this size would have to commit resources over a period longer than any human institution has ever sustained continuously. The pyramids of Egypt were built over about 80 years. The great medieval cathedrals took 2 or 3 centuries, but they were built in just one place, with generations of craftsmen taking turns on solid ground, with the structure visibly growing over time. Interstellar travel offers none of that. It's invisible progress within invisible emptiness, sustained by people who will never see the destination, in the name of a goal that won't be achieved by anyone who remembers why it was chosen. The departing crew has trained for years and understands the mission. They carry its weight willingly, perhaps even with pride, the way the first generations usually carry purpose as a gift, not as a burden. They are the ones who chose. Their children didn't choose anything. They were born during the journey. They've never truly felt gravity except for what is simulated by some rotation system on the ship. They know the mission the same way anyone knows the circumstances of their own birth, as a given condition, not as a decision made. They can honor this mission. They can also, over time, resent it, develop their own priorities, their own internal politics, their own ideas about what the ship is really for and who it truly belongs to. Not even communication escapes this cruel arithmetic. Even if the ship maintained a perfectly functional radio or laser channel throughout the entire journey, which would already be in itself an engineering feat sustained for decades. Each message sent back to Earth would take at least the same 4.24 years to arrive. Traveling at the maximum speed the universe allows, the speed of light, a question sent from the ship would receive an answer, at best, almost 9 years after it was asked. Conversation is impossible at that pace. There are only isolated, chronologically disconnected messages that arrive like capsules from a past that, on the other side, no longer exists in that way. The child who was born on board and sent a message about their first birthday would already be closer to adolescence by the time the reply, full of affection but long delayed, finally arrived. 3 generations after departure, the entire crew is made up of people for whom Earth is mythology, for whom the scientists who designed the mission are distant historical figures, for whom the destination is an abstraction, A star that gets just a little bit brighter every year, still decades away. What keeps these people loyal to the mission? That's not a question with an engineering answer. It's a question about the endurance of human purpose over time. And history, when examined honestly, doesn't offer much comfort. Institutions fragment, priorities dissolve, and the meaning that animates a project in the founding generation tends to fade as the founders disappear. As a species, we've never maintained a single, coherent institutional purpose over 3 generations without profound transformations in the original intent. A generation ship is not just an engineering project, it's a society. A closed society inside a hull with no immigration and no emigration. No external culture to renew its ideas. No physical frontier to absorb its own internal tensions. Every conflict needs to be resolved within the same walls that created it. We have no real example in human history of an entire civilization isolated for centuries within a closed space. We truly don't know what a society like that becomes, so the problems pile up. Physics on top of engineering, engineering on top of biology, biology on top of the very architecture of a civilization. Each layer is a wall, and each wall only becomes visible after the previous one has finally been understood. At the end of all of them, the star is still there, silent 4 light years away, neither closer nor farther, for having been so minutely and meticulously studied. It simply waits the way distances wait, without hurry, without any awareness that someone is waiting for them in return. If you go out tonight and the sky is clear and you know exactly where to look, you'll find a little dot of light in the direction of Centaurus. Nothing special at first glance, indistinguishable from the thousands of other dots around, unless you have a map and patience. Just an old, steady light that had already been traveling for 4 years before you started reading this text. That light doesn't know it's a destination. It doesn't know that a species on a small planet in a neighboring system spent decades calculating the cost of crossing the void between them and found out that the numbers don't add up. It just keeps burning, as it has for billions of years, fusing hydrogen into helium, spreading light equally in all directions, indifferent to whoever receives it on the other side. The distance between here and there is not a challenge set by the universe. It's not a test nor a barrier placed on purpose, waiting for a solution that's smart enough. It's simply the scale at which the universe operates. The same scale it has always operated on, long before anything existed that could consider this scale too large. We are creatures just a few meters tall and with only a few decades to live, looking at distances that span centuries and energies that would outshine entire civilizations. And maybe the very act of looking is already the most remarkable part of all this. Not the crossing, but the looking. The fact that something assembled from the dust of an ancient stellar explosion can, today, calmly sit on a warm world and feel the weight of a distance that, most likely, it will never cross. The question in the title now has an answer, but it's not a single answer. It's a layered answer, built from physics, biology, fuel and time, and the fragile architecture of human purpose. What would kill you first on the journey to Alpha Centauri depends on how far you manage to get. Radiation starts to take effect from day one. The body begins to forget what gravity is within a matter of weeks. In practice, the fuel runs out even before the journey begins. Generations blur together at some lost point in the middle of the journey. And the meaning, carried so carefully on the day of departure, becomes harder and harder to sustain with each passing year in the void. But you're not on that ship. You're here on this side of that distance, in a world where the universe owes no explanation to anyone for being so hard to leave. Beneath your feet, there's an entire magnetic field working for free, without you having to think about it, deflecting particles that would pass through bodies effortlessly anywhere else. Above your head, there's an entire atmosphere, A thin layer of air that, seen from afar, seems almost too fragile to protect anything, and yet even so is exactly enough. None of these privileges were earned. They were simply inherited for free because we were born in the right place in space, at the right time in the history of an ordinary star. It's strange to think that much of what usually makes us feel small in the face of the universe, the darkness between the stars, the silence, the distance, is exactly the same set of things that, down here, never even comes close to us. The star is still 4 light years away. It will stay that way for a long time, probably forever, within any time frame that makes sense for a human life. And the light it's sending your way now will only arrive long after everything else has changed. After this video's over, after the night in which you're watching it has passed, after much of what seems urgent today no longer matters. This is the crossing. That's all the crossing has ever been.